Hey Chem 100, this is Dr. Ricardo. This is the last video for Chapter 10. Chapter 10 is bonding, and we're up to page 14 of the notes. So what we're going to talk about for a little while, even though we're not going to stress it on the exams, is the idea of an expanded octet. So if you think about the very first row of the periodic table just observes the two-tet rule. And the reason it is, which elements are we talking about? The first row of the periodic table is hydrogen and helium. Well, they can't have an octet because they don't have any p electrons, right? If you're in the first row of the periodic table, when we learn the quantum mechanics and the electron configuration, the only thing that you're allowed when the principal quantum number is equal to 1 is you're allowed to have an s orbital. So hydrogen is 1s1, and helium on the other side is 1s2. So they can't possibly have 8 because when you're in the first main group or the first principal energy level, you can only have a maximum of 2 total electrons. Then you get to the second group, which starts with lithium and ends with neon. They do have the possibility for an octet because which atomic orbitals do they have to mix in? They have the 2s, right? 2s2, and then 2p, which has 6 members, and you can go all the way up to 2p6. So that's how you get to 8. So beyond that, when you get to the third group of the periodic table, although they don't take advantage of it much, in the third group of the periodic table, there is a third kind of orbital. There's not only s's and p's, but there's empty d orbitals that usually don't fill up until after the 4s fills up, but they're still there and they're empty. So elements in the third row of the periodic table do have the opportunity on special occasions, okay, when there's so much electron density around, to break the octet rule and go more than 8. So let me give you an example of that. So first row strictly fills up the 1s orbital, so that's hydrogen and helium. Hydrogen has 1 electron, it's looking for 2, so it only tends to bond once. We call that a pendant atom. Helium doesn't look to bond at all. It's looking for 2, right, to fill up its 1s. It naturally has 2, so helium is one of the least likely elements to ever get involved in a chemical reaction. It's already happy with a completely filled up 1s orbital. When you go beyond that, elements in the second period are restricted to filling up their 2s and 2p orbitals, and they strictly have to obey the octet rule. No way around it. Okay, one example is oxygen, which is 1s2, 2s2, 2p4. These these two sets, this 4 plus 2, 6, is the 6 valence electrons that it has available to bonding. These are core electrons that can't be used. In order to be valence electrons, you have to be in the outermost principal energy level. So only things with a 2 as a coefficient are going to count. So those 4 electrons count for valence electrons plus these 2. Okay, so if we were going to draw that, the 1s is buried, but you can think of mixing in the 2s, okay? And here's the 2p's, and the 2s would be filled up with 2 electrons, and the 2p, you would give everybody 1 before you give anybody 2, so that's how it would be. So the reason why oxygen loves to bond twice is this one is looking to overlap and this one is looking to overlap. Okay, so it has a tendency to bond twice. There's no such thing as a 3D, so it can't go beyond using this one as a bonding site and using this one as a bonding site and taking its 6 natural electrons up to 8, because the 2 extra electrons would be coming from the other atom that it's sharing electrons. So this orbital would be for sharing, and this orbital would be for sharing. Okay? It does something called the hybridization first, but you kind of get the idea. There is no such thing as a 2D, so you can't break the octet rule. But let's take sulfur, which is right underneath oxygen on the periodic table. Here's the reason why it can break the periodic rule. It has 16 valence electrons. 10 of them are in its core, right? So those are going to be core electrons. It's 1s2, 2s2, 2p6. Since they have coefficients of 2, they're never going to count as valence electrons. It's only the ones with 3 or higher. Okay? So what does sulfur have? It has 10 just like neon, then it has 3s2, 3p4. So this 4 plus 2 is 6, plus 10 gives you 16. And even though we don't usually write it, it has an empty 3d orbital. So if I fill up all of the valence electrons, the 3p fills up, the 3s fills up, then the 3p. I put 4 electrons in there, so I give everybody 1 before anybody gets 2, so I get 1, 2, 3, and then there's the 4th one. And now I have these empty ones up here. So not only can this one overlap and this one, and that would give me a total of 8 valence electrons, right? 2, 4, 6, 8. But what happens if the other atom is bringing in electrons? Well, you can actually use one of these 3d electrons for bonding. That would give it a total of 10 valence electrons, or 2 of them even to give it 12. So there are cases where atoms in the 3rd group of the periodic table or more can have 10 valence electrons because they take advantage of the empty 3d orbitals that they have. Okay? I've even seen things go to 14 or 16, but 10 and 12 are more prevalent. Okay? Here's an example. We're going to do a comparison of 2 molecules of phosphorus and fluorine. Okay? One that you would expect where fluorine behaves by the octet rule, and one where it breaks the octet rule. So the 2 compounds we're going to look at are phosphorus trifluoride and phosphorus pentafluoride, which both exist under different conditions. Okay? So if you really swamp the phosphorus with a lot of fluorine and put it in conditions where there's a very high fluorine concentration, and you also do it at low temperature, you can force the reaction all the way to PF5 rather than the expected PF3. Okay, so let's do everything that we would normally do for PF3. So if I do PF3, first thing I always have to do is count up the total number of valence electrons. Phosphorus is in the 5th row across of the periodic table. So there's 1 phosphorus. 5th row means it has, 5th column means it has 5 valence electrons. How about fluorine? There's 3 of them. They're in the 7th column. So they have 7 valence electrons. So that gives us 21. So we wind up with a grand total of 26 valence electrons in there. Okay? Well, let's put them around. The phosphorus has to be in the middle. Why? Because fluorine has 7 valence electrons, and plus fluorine tends, like hydrogen, to only bond once. All of the halogens tend to only want to bond once. Not only fluorine, but chlorine, bromine, iodine, all of these things. What's your expectation? Your expectation is that they're just going to have a single bond, and the rest are going to be lone pairs around it. They're going to follow this model. I won't do it for every single one, but there's going to be a single bond with 3 sets of lone pairs to give it 8. Well, fluorine definitely can't break the octet rule. Why? Because it's in the 2nd group of the periodic table. Here's phosphorus, though. It's in the 3rd group. Maybe it can, depending on the situation. Okay? So, other reason why phosphorus is going to be in the middle compared to fluorine, if you are further to the right on the periodic table, you are more likely to be a pendant atom. If you're further to the left, like phosphorus, you're more likely to branch and have multiple bonds to you. So a choice between phosphorus and fluorine, it's going to be the phosphorus that's in the middle. Just like a choice between carbon and oxygen, the carbon's in the middle. If you're further to the left on the periodic table, you're more likely to be in the middle. Put the 3 phosphoruses around it, the 3 fluorines around it. They have to make at least a single bond, otherwise they wouldn't be in the same molecule. Well, that takes up 6, right? I've got 20 more. Where do I always start? Don't start on the inside. Only put them on the inside when you need to. Start on the outside. 2, 4, 6, 8. Has an octet, happy. This one already has 2, 4, 6, 8, happy. 2, 4, 6, 8, happy. How many did I get to? I got to 24, right? 8 times 4. So where does the last 2? Perfectly right in there, giving not only phosphorus a octet, but each of the fluorines has an octet. So this is our expected Lewis electron dot diagram, a Lewis diagram for phosphorus trifluoride. Okay, how would they be arranged? Well, I have 4 total groups. So whenever I have 4 total groups, what did we just learn? The electron pair arrangement is said to be tetrahedral. Okay? What's the molecular shape when I have 4 total groups, 3 of them are bonding, and 1 of them is a lone pair. Well, we learned that that was just like ammonia. That has the really cool thing that it's called trigonal pyramidal, not bipyramidal, trigonal pyramidal. So it's the phosphorus that we think of in the middle. We kick this guy straight out and this guy straight up. Those are the first 2. You can think of the lone pair up here, right? And where are the other 2 fluorines? This one is not only down, but popping out of the blackboard, popping out of the paper. And this one is down and in the back of the paper. And that would be the shape. So it's a tetrahedral shape where the top is a lone pair, so we don't count that. So let me circle it in yellow, just the part where that outlines the atoms. Look at that, just the part that outlines the atoms. So the molecular shape is trigonal bipyramidal. What's this bond angle in here? 109 degrees, and that's the bond angle associated with anything that has an electron pair arrangement of tetrahedral. Okay, so we did that one. Nothing new, nothing unexpected. The cool one, though, is phosphorus pentachloride, if I put 5 around them. So let's go ahead and do that. If I have to do PF5, first step, count up the valence electrons. Phosphorus, 5th column of the periodic table when I ignore the transition element, so 1 times 5. Okay. Fluorine, 7th row of the periodic table, and there is 5 of them. That gives you 35. So 35 and 5, wow, there's going to be total of 40 electrons in my picture. Phosphorus has to go in the middle. Fluorine never goes in the middle. Fluorine is only looking to make 1 bond. Well, if I have to put 5 things around it, why don't I start with something that kind of looks like home plate, right? Put 4 and 1 up here, and then later on, we'll decide the shape. Well, if all of these things are in the same molecule, and I can't have any little triangles, right? Because fluorine never bonds twice, right? So I can't bond a fluorine to a fluorine because then I'm done. So the fluorines have to be attached directly to the phosphorus, and they are. So that uses up 10, right? Well, start on the outside. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Think top, bottom, left, right for each of these. Okay, if you count them up, you will get 40. Every fluorine has an octet, nice and happy because it's sharing these 2. Every phosphorus has 10 around it, right? 2, 4, 6, 8, 10. This is the only arrangement that could possibly make this. So we have to have an expanded octet, 10 electrons around the phosphorus. Okay, well, let's talk about the shapes. Whenever we wrap 5 things around one, we did something really, really cool. We have the central atom, and then we make a little triangle in the plane. This guy's straight out. This guy is like a triangle coming out and popping directly out of the blackboard, not going down, just popping out of the blackboard, and this guy's behind the blackboard. So think about, let me get a pencil. Think about a triangle in the plane of the paper, right? So if I did this, a triangle in the plane of the paper, and one coming straight up and one coming straight down. This is the way that nature arranges 5 things. This is the only shape that nature uses that uses 2 different bond angles. I have a peace sign around the triangle in the plane. So this is a bond angle between here and here of 120 degrees. And then between that flat plane and the ones that are coming up and down, right, that makes a right angle. That's 90 degrees. So think about like this sort of flat triangle, one up, one down. That's the shape. So if you're going to answer the questions around it, this is the Lewis electron dot diagram, right? What is the electron pair arrangement? The electron pair arrangement is called trigonal bipyramidal because it's a double pyramid, one pyramid up and one pyramid down. This last one was just trigonal pyramidal. Right? I just had the pyramid, this flat pyramid down here, nothing up there. That's called trigonal bipyramidal, and we learned that in the last section. And last thing, what is the molecular shape? Whenever there are no lone pairs around the central atom, only bonding pairs, I have 5 single bonds. Whenever that's the case, there are no lone pairs around the central atom, the electron pair geometry will be exactly the same as the molecular shape. There's nothing to ignore. Trigonal bipyramidal. Okay, that's what I have over here. Just me drawing it much nicer. Right, 2 different bond angles, 10 electrons around the central atom. Okay, last example. We're going to actually make a chemical compound out of a noble gas, right? You couldn't do this with helium, but if you go way down the periodic table all the way to xenon, somebody actually won the Nobel Prize for making these kinds of compounds. You can force xenon under very special conditions of high pressures of fluorine, right? At very cold temperatures, you can make xenon compounds, even though xenon already has an octet. So imagine that. We're going to take a noble gas and get it to react. So let's see what happens. So this compound has been experimentally made. It's called xenon tetrafluoride. So let's go through our analysis and figure out what would be the best arrangement of those electrons. Okay, well, like we said, there's one xenon, and it already has an octet, but it's getting involved in chemical bonding anyway, right? This is a super exception, a noble gas that makes a chemical. All right, and the fluorines, like fluorine is so reactive. 4 times 7 is 28, 36 electrons in my picture. All right, the fluorine can never be in the middle, right? Xenon is got to be in the middle because fluorine can't break the octet rule. Xenon can because it has unfilled d electrons. Which ones are going to be donating in now? If I'm in the 5th group here, right, it's going to be its unfilled 5d electrons, okay, that are going to participate in the bonding. Okay, I have to put the 4 fluorines around it, so why don't I just make it like a cross to start with? 1 up, 1 down, 1 to the left, 1 to the right. Only that was left, that was right. Okay, they have to be in the same molecule. The fluorines can't bond to themselves because they can't break the octet rule. How many have I used up so far? 2, 4, 6, 8. Well, keep it going. Always start on the outside first, right? You got to get all the way up to 36 and you're only at 8. So 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Whoa, 32, but I still have 2 more pairs of electrons. They can't go around any of the fluorines because they can't break the octet rule, so they actually have to super unbelievably overload the xenon. And the xenon is not only going to have 4 single bonds, it's going to have 2 lone pairs of electrons coming out of it. Okay, well, that looks pretty cramped in there. These electrons are going to have electron density that's going to want to get away from each other. What's nature's natural shape? Well, we said the shape when I have a total of 12 electrons would be 6 groups of electron density. How would 6 things naturally get away from each other? Well, this one is common sense to us. I would put 1 thing in the front, 1 thing in the back, 1 thing on the top, 1 thing on the bottom, 1 thing on the left, 1 thing on the right. So I'm going to rearrange this, and I'm going to draw the xenon in the middle, okay? And I want you to think about a flat plane. So right over here, I'm going to make 1 bond. This guy is coming in the back of the xenon and going, okay, not up or down, but just in the back of the paper. And this one is coming out this way in the front of the paper. Right now, these 2 guys are making a straight line. One's in the back of the paper, one's in the front of the paper, okay? This one, front of the paper. This one, back of the paper. So I just made a cross in the plane, in the flat plane. Just think of the xenon sitting like this, okay? So these guys are flat in the plane, okay? So where's my electrons? The last two pairs, this pair and this pair, are going to be one up and one down. They take up a lot of room, the unpaired ones. They're bulky. So I draw them big. So they want to get away from the bonded ones, so they won't go like 90 to 90. I won't put like one of this balloon of electron density next to a balloon of electron density and I'm smashing into each other. These two balloons of electron density, one goes on the top, one goes on the bottom. And then this is a cross in the plane. Okay? All right, well, what are you going to call this? Well, if you fill in this box over here, this box in the plane, right? Try to think about that as that's flat. And this guy is kind of on the top. Right? You can see it a little better if I erase some of this. Make it like negative space, right? Like when you learn in art, right? That guy's on the top. This guy is on the bottom, so I can't see him. He's on the bottom, he's on the top, right? But what would you call that? This one is called square planar. When I have 4 bonding groups, right? Groups to 4 atoms. This is to an atom, 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 and 2 lone pairs. Okay, what's the electron pair arrangement? Anytime I have 6 things wrapped around one, octahedral. What's the bond angle associated with octahedral? All the bond angles are 90. But what's the molecular shape? When of those 6 groups of electron density, they're not all bonding groups. If they were all bonding groups, this would be octahedral and this would be octahedral. This we call square planar. It makes a flat square of atoms with electrons up and down coming off of the xenon in the middle. So here's a nicer picture of it. 36, have to break the octet rule. 4 single bonds to 4 fluorines, 1 lone pair up, 1 lone pair down. All the bond angles are 90. Remember, it's only this shape, this wild shape, the triangle with the one on top and one on the bottom, trigonal bipyramidal, that has 2 distinctive bond angles. Everything else we learned in the last video had 1, right? Tetrahedral, the bond angle for that electron pair arrangement was always 109, right? Trigonal planar was just a straight old-fashioned triangle, so that would be 120, the angles between the 3 things in a triangle, and linear would be 180. So we have 180 for linear, 120 for trigonal planar, 109 for tetrahedral, 2 bond angles for trigonal bipyramidal, 90 and 120, and only 1 bond angle for octahedral, right? Just a typical expectation. In the back, make a square plane, 1 on the top, 1 on the bottom. So you could think about this: top, left, right, back, forward. Okay, or whichever way you want to say that, right? You say this is sort of the front left, back right. They go straight across, right? That's a 180. This is 90, 90, 90, 90 that way, 90 around to here. Everything's 90. Okay, so that's it for this discussion. The only thing I want to do now is just go through a couple of not exceptions, but how do you do some ions? So let's do the following 4 ions before we stop. So we're going to do sulfate, ammonium, carbonate, and cyanide. Okay? So these are polyatomic ions that you guys already have memorized their names. Let me show you how to answer the questions, right? So what are the questions? Draw the Lewis electron dot structure. What's the electron pair arrangement? What's the molecular shape? What's the bond angle? Okay, so first thing, SO4 minus 2. Okay, first thing you do, count up the valence electrons. You need to know how many electrons are participating in the process, right? The core electrons can't. So there's 1 sulfur. Where's sulfur on the periodic table? 6th column over. Where's oxygen? Right on top of sulfur, so it also has 6. There's 4 oxygens. So that's 24, right? And then, don't forget, this is a sulfate ion, so it has 2 extra electrons. So you need to add 2 extra that come from the 2 electrons. Okay, so I get 24. We could do it this way. 24 plus 6 is 30, plus 2 is 32. So there's going to be 32 in the picture. Okay, got to be the sulfur in the middle. You're not going to usually find oxygen in the middle, and I can show you that on the periodic table. Right? Same, if you're in the same column, then further down is more likely to have branching. So sulfur is more likely to have branching than oxygen. So to the left is even better, right? So if phosphorus compared to oxygen, that's a no-brainer. But even sulfur is going to have more branching than oxygen, because the further down you are, the more likely you are to branch. So to the left is more likely to be in the middle, and down is more likely to be in the middle. So sulfur beats oxygen. That means the oxygens are on the outside. So do a very simple arrangement originally. Later on, we'll figure out what the shape is. They have to, the 4 sulfurs have to be bound to the oxygen, so put them around. Make a single bonded network. They have to all be attached. No little triangles, because that would break the octet rule. How many do I have so far? 2, 4, 6, 8. Got to get to 32. Start filling them in. Top, bottom, left, right. There's 2, 4, 6, 8. 2, 4, 6, 8. That's 16. 2, 4, 6, 8. That's 24. 2, 4, 6, 8. That's 32. 8 times 4. This is a totally symmetric ion. The sulfur has an octet with 4 single bonds. Pretty boring. Each sulfur, each oxygen has a single bond and 3 lone pairs. So this has an octet, and happy, every one of these, it has an octet in the same way. 3 sets of lone pairs and 1 single bond. Sulfur, just like carbon normally has, 4 single bonds. Okay, that's the Lewis structure. Next, what's the electron pair arrangement? Count up the total number of bonding groups around the central atom. 1, 2, 3, 4. 4 things wrapped around 1, that makes a tetrahedral shape. What's the bond angle of all tetrahedrals? 109. What's the molecular shape? Whenever there are no lone pairs around the central atom, there's nothing to ignore. So the electron pair arrangement is the same as the molecular shape. It's also tetrahedral. So you would picture this thing looking a little bit more like this. 1 oxygen out, 1 oxygen up. This guy coming out of the blackboard a little bit. This guy back behind the blackboard. A little more like a tripod than this, right? This is what how nature would arrange it. Good? And what are the bond angles? These are all 109s. Okay, so that's the first one. Nothing fancy, nothing surprising. Okay, ammonia I think we've done already, but we'll do it again. NH4 plus 1. Where's nitrogen? 5th column over. 1 times 5 gives you 5. Where's the 1 from? There's only 1 in there. Hydrogen. There's 4 hydrogens. Each one has 1 valence electron. This gives you 4. So right now I have 9, but it has a plus 1. So the plus 1 means, how does something become positive? If you take 1 electron out. I need to take 1 out. That gives me 8. So ammonia only has 8 valence electrons. It would have had 9 if it was NH4, but since it's NH4 plus, it has 8. Hydrogen never goes in the middle. It's a pendant atom, which can only make a 2-tet. So put the nitrogen in the middle, right? Each hydrogen has to make at least a single bond. Sorry, I lost my screen. You guys are still going, which is good. Okay. There's my 8. 2, 4, 6, 8. Nitrogen is totally happy with an octet. Each hydrogen is happy with a 2-tet. That's done. You got your 8 in the picture. The only thing you want to tell the world is this bad boy has a charge. So you put parentheses around it and you say +1. The whole thing is +1. Okay, let's answer the questions. Electron pair arrangement. 4 things wrapped around the central atom. It's called a tetrahedron. All tetrahedrons have a bond angle of 109 degrees. What's the molecular shape? Whenever there's nothing to ignore, there's no lone pairs. Also tetrahedral. These 2 things will agree when there's no lone pairs around the central atom. Not only does ammonia not have any lone pairs around the central atom, it doesn't have any lone pairs, period, right? Because hydrogen can never have lone pairs. Each hydrogen is happy with its 2 tet, right? This guy's happy with 2, happy with 2, happy with 2, happy with 2, and the nitrogen, happy with 8. It's okay to double count in this one case, right? You're double counting because sharing allows you to count them twice. Good, that's the answers for ammonia. Okay, let's do carbonate quickly. So carbonate, I'm going to do CO3, and then I got to add 2 extra electrons to it. It's going to have 2 more than CO3 would. CO3 is unstable, right? In gas phase chemistry, carbon forms bonds with 1 oxygen and 2 oxygens. Once it goes to form with the 3rd one, it also removes 2 electrons from someplace. It gets 2 electrons from something else because this is stable, whereas CO3 isn't. It's the 2 electrons that help. So this is a very important polyatomic ion, carbonate, right? So you know this from the very beginning of the year, you've memorized that. Well, let's see what its structure looks like. Okay, here goes carbon. 1 times 4. Carbon is a 4th column over on the periodic table. Oxygen, we've been doing a lot of oxygens. Oxygen, there are 3 of them. Each one has 6. That gets you to 18. Plus the 2 extra electrons, right? I don't add them on. Excuse me, I add 2 extra on from there. That gives me a total of 24. Okay, I'm going to go back to that sulfur one just because I did forget one little thing in the sulfur. When I was doing this guy up here, I should have put the brackets around and said this whole sulfate is -2, right? When you do an ion and you do the Lewis structure, if it has a charge, put brackets around it and put the charge in the upper right-hand corner. Just like I did for the ammonia. Okay, so do that. Here I did it for the ammonia. Whenever it has a charge, do that. Okay. Here's carbonate. Carbon's got to go in the middle, further to the left than oxygen. 3 oxygens, so make a little triangle. Why not? Right, spread them out. Everybody's got to have at least a single bond to the carbon, otherwise they wouldn't be in the same molecule. Right? You're not going to go across here. That would break the octet rule. Now, what do you do after you make the single bonded network? Put the extra electrons around the outside first and only push them into carbon when you need to. Okay, I've got 24. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. There's my 24. Each oxygen is happy with a single bond and 3 lone pairs, right? But the carbon is not happy at all. It only has 6 valence electrons around it. It's striving for 8. It's in love with 8. So you would be better off by taking one of the pairs of electrons, either from this one and donating them in to make a double, or from this one, or from this one. At this stage, it doesn't matter. Just pick one of them and you'll get to an octet. So these would be better off donated in to use as a multiple bond. You need multiple bonding to give everybody an octet in carbonate. Okay, the bottom 2, nothing happened to, so I'm going to leave those alone. Okay, here though, I had 3 lone pairs and a single bond. If I donate these electrons in and use them as a bond, I only have 2 up here. Okay, if you count everybody up in here in carbonate, you'll get 24. Okay? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and each atom has an octet. This carbon in the middle is super happy with a double bond and 2 singles, because it has 8 total valence electrons in its sphere. 2, 4, 6, 8. That's what makes it happy. Okay? This oxygen, even though it donated in a pair of electrons, is still content, because check it out. 2, 4, 6, 8. When you share, you feel good. Right? So rather than hogging those up to yourself, share them. Good? Okay. You need to put the brackets around here and tell the world this whole thing has a -2 charge. So you put brackets around the ion. So this is the Lewis structure. Now we have to answer the questions. Okay, first question. What's the electron pair arrangement? How are those electrons arranged? How many total groups of electron density, not bonds, groups of electron density around the central atom? Remember, a double bond counts as a single group of electron density. These guys are headed towards the same atom. They're not repelling each other. But those are going to be repelled from this group and also from this group. So this has 3 groups of electron density. When 3 things wrap themselves around one, it makes a trigonal planar arrangement. All trigonal planes, it's just a regular flat triangle, have bond angles of 120 degrees. Are there any lone pairs around the central atom? No. All of these lone pairs are on the outside atoms. So there's nothing to ignore. This would look exactly like you see right here. It would look like a totally flat little peace sign or a triangle. Completely flat, right? I got nothing up here, nothing underneath. Nothing's popping out like in those other pictures. This is just a flat, very flat molecule. Okay, whenever there are no lone pairs around the central atom, the electron pair arrangement is the same as the electron pair, as the molecular shape. So this would also be trigonal planar. Good. That's the kinds of questions you're always going to have to answer. Draw the Lewis picture, answer the questions. Electron pair arrangement, bond angle, go together. You can just memorize those 2 together. And then molecular shape, you have to ask one more question. What would it look like if I leave out the lone pairs around the central atom? These will be identical when there are no lone pairs around the central atom. Okay, last example from page 16. What about cyanide? Okay, so this is the cyanide that you're thinking of. This is the poison. It can be delivered in the form of hydrogen cyanide gas, sodium cyanide, potassium cyanide, but this thing right here is called cyanide. Okay, it's the polyatomic ion Cn-1. So let's do it. There's 1 carbon. It's got 4 valence electrons. Carbon always has 4 valence electrons. 4th group over from the left when you leave out the transition elements. Nitrogen is 1 more column over. It's got 5. So 4 and 5 make 9. We never seem to have any odd numbers. Kind of curious. And why the 1 extra electron? Because of the negative charge. Right? Negative means extra electrons. So 9 and 1 is 10, plus 4 is 14. All right, the C and the N are in the same molecule. Got at least to have a single bond. All right. Why do I do that? Well, there's nothing in the middle. This could be in the middle, this could be in the middle. You only have 2 things, so you don't have to ask the question, who's in the middle, right? If there were 2 ends, right, it would be the carbon in the middle because it's further to the left on the periodic table. But when you have 2 things, that's it, right? So this thing in the end, it's going to have a molecular shape that's linear because 2 things make a line. So it can't possibly be anything else. You would need a 3rd atom to make a bond, okay? So the bond angle isn't even an important question, right? You need to have a 3rd thing to figure out which way it's pointing. So 2 things always have to make a straight line. Okay, let's put the electrons around that though. So far it's got 2 in there and I have 12 more to go. So start on the outside first. 2, 4, 6, 8, 10, 12, 14. Okay, there's 14 in the picture, but carbon's not happy, right? And nitrogen is not happy. Oh, guys, I don't know what the heck I was doing. Sorry, this is not 9. 5 times 1 is 5, right? This is 1. Okay, so I'm going to wind up with 10 in the picture. Sorry about that. So if I have, right? So if I have 10 in my picture, I'm going to run out a little quicker. So there's my 2. 4, 6, 8, 10. Okay? So I could either do that or I can make it symmetrical and put those over there, but I'm going to wind up with the same answer. Okay, take a look. This arrangement, this carbon is happy with 8, but this poor carbon over here only has 4. This nitrogen only has 4. So these would be better off by helping out and donating in. Well, what does that get you? That gets me a little better. Now I would have this. Still not done. This carbon is okay. 2, 4, 6, 8. This nitrogen, though, only has 2, 4, 6. So what could I do? Take another pair. Right? So the reason for making multiple bonds is use the electrons in a better way so that if you share them, both parties can get to an octet. So if I push those guys in, there's only one set left over here and one set left over here. A very tight little symmetrical molecule. And I got to tell the world that it's got a -1 on it. So I do it that way. So this is the correct answer. Right? What is the Lewis structure for cyanide? That's it. This carbon is happy with an octet, 2, 4, 6, 8. This nitrogen equally happy with an octet, 2, 4, 6, 8. Okay? All right, let's answer the questions. These are trivial, right? What is the electron pair arrangement? Well, there's 2 total groups around, there's no central atom. Oops, sorry, not TD. The electron pair arrangement. The electron pair arrangement is going to be linear. This electron pair is going to want to get away from that triple bond. That's a group of electron density, that's a group of electron density. They're repelled from each other. So these dots are not going to come up on top and be close to that triple bond. They want to get as far away as possible. Same thing with this triple bond and those 2 dots. They want to get as far away as possible, right? It's got to be linear. Things want to make a straight line to get as far away from possible. This hates this, and this hates this. So put something in the middle. Put the atoms in the middle. Okay. Plus, 2 points make a line, so this has to be straight. Okay, electron pair arrangement. First, molecular shape second. Okay, again, yes, there's lone pairs here, but there's not another atom anyplace. So this also is going to be linear. Okay, and even though this is a trivial question because 2 things have to make a straight line, if I did it with the dots, those dots would be there as opposed to twisted around. So the bond angle is also 180 degrees. 180 degrees will always go with linear electron pair arrangement. Okay? All right, so those are all of the examples that I have, and that is it for Chapter 10. Thank you.